So let's get started. Today we'll talk about chapter 6 of the book, population models. So we're going to start thinking about rabbits, wolves, sheep, animals eating each other, eating grass in an island, not island, whatever. So the simplest population model you can think of is the same population model we use for the bacteria. Which one is that? What is the simplest model? What is it?
Exponential growth.
Exponential growth. Okay, so the first type of model that I'd like to discuss with you is, once again, exponential growth. And by the way, we're going to cover section 6.1 today, single species populations. So today we're going to talk about just models of one variable, where there's only one variable over time. So just like before, we're going to call n of t the population over time. Over time. So think about your favorite animal. Krista, what's your favorite animal?
Giraffes.
Okay, this is a population of giraffes. And it's growing over time. So think about giraffes in a desert. There's plenty of food and there's plenty of space. So how do the giraffes grow over time? It's just constant times n. Okay? So, can anybody explain to me what this constant means? First of all, what units does it have? We said that before. 1 over time, right? It's the unit of this r. And in a sense, it describes how fast the population grows, but not quite, right? I mean, the rate of growth is r times n. So how would you describe r by itself? It's the rate of growth per individual, you know? Like r is equal to n prime of t divided by n of t. Right? It's like how fast each individual on its own is contributing to spread the population. Does that make sense? Right? So this is something like the rate of growth per individual. We'll call this the intrinsic growth rate. Okay? So intrinsic growth rate means per giraffe, how fast does a giraffe reproduce, for example, making 2 giraffes. Okay, so let's make this a little bit a lot more complicated, because we've already talked about exponential to death. So now our giraffes live in an island, okay? And there's only so much space for the giraffes. So how do we now take into account the fact that there's only so much space? Well, we do the same thing as before, r times n, okay? But now we multiply this by a term. And this term is going to be 1 minus, does anybody know? N divided by a constant, actually. Okay? Think about this constant as some large number, let's say 1,000. So this island can only hold about 1,000 giraffes. Okay? So, and this is a funny way to write it, but let's think about how this works. And I may have said this before. I'm not sure exactly how detailed we said this. When the population is small compared with C, okay, then this number, Rn 1 minus n over C, this number is small. N over C is small, right? So 1 minus something very small is basically still 1, and this is roughly equal to r times n. So we end up with the original model, right? But as n approaches C, this number starts growing, right? And when n becomes very, very close to c, this number becomes very, very close to 0, so the population slows down. What you see then is this phenomenon. Over time, this is n. Suppose this is c right here. In the beginning, the population starts growing exponentially. Exponentially. Now, the population growth, the exponential population growth model will do like this. The logistic growth model starts the same, okay, but then at some point starts slowing down and starts converging towards C. So this is exponential, and this is logistic. And C is what's called the carrying capacity, because there cannot be no more giraffes over a long time period than C. In fact, if you started out with more than C giraffes, then the population would start shrinking and converging towards C. Okay? I think we did this something like this in the first lecture or something. So there you go, exponential versus logistic. So let's think about what we did. I'm going to call this section intrinsic growth rate. So suppose that you have a general formula for the growth. Okay? Some nonlinear function, f of n. Now, one principle that it's pretty important in biology is that if you have no giraffes, there cannot be any giraffes being born. Okay? They gave it a fancy name, the axiom of parenthood or something like that. But if you have no giraffes, you can't breed giraffes, right? That's why there's no giraffes around here on campus, because there wasn't any giraffes here a few months ago, right? There's also no anteaters. I don't know if there's any real anteaters around here, but I don't think so. Just statues, that's right. So the axiom of parenthood says that, how would you describe this mathematically? If there's no giraffes to begin with, you cannot have any rate of growth of giraffes.
An initial condition, f of 0 equals 0.
Exactly, f of 0, okay. So notice that f of 0 is equal to 0. If there's no giraffes to begin with, the rate of growth is 0. That is, no offspring can come out of no individuals. Okay. Now, something that you can do with a function that starts out at 0 is the following trick. Since f of 0 is equal to 0, we can write, and you tell me what you think about this trick. F of n is equal to n times g of n. What do you think about that trick? Basically, we're essentially factoring out an n out of this function f to create another function g. What do you think of that? Is that always possible to do? So for example, if f of n is a polynomial, say a0 plus n a1 plus n squared a2 until n to the, I don't know, m times am, can we factor out an n in there? Well, but remember, f of 0 is equal to 0, right? Since f of 0 is equal to 0, that means that a0 is equal to 0. Right? So we can factor out an n. So f of n is equal to n times, and then the function n a1 plus n a2 plus n to the m minus 1 am. And this thing over here is our function g of n. Okay? So for polynomials, we can do this. We can factor out the n. Now, we can actually do this for in more generality. If you take the function f and you write it using a Taylor expansion, using an infinite polynomial, okay, then you can factor out the n and write it as n times g of n. So same procedure can be used for any, and then the technical term is analytic. For any analytic function f. Okay, you write f as a infinite polynomial. So a0 plus a1n plus a2 n squared, and so on and so forth. And because a0 is equal to 0, we can write this as n times a1 plus n a2 plus. Okay, so why am I insisting so much on writing this as n times g of n? Well, because this thing is called the what?
Intrinsic growth.
That's right. It's the same as the r here, right? N prime is equal to n times something. Okay? N prime is equal to n times something. So, once again, g of n is the intrinsic growth rate. Okay, now what's the intrinsic growth rate? Well, so again, the intrinsic growth rate in a sense is like the happiness level of the animal. It means how fast it's able to divide, right? It's very different from f, right? It's not the same as f. F is the growth rate itself, and g is the growth rate per individual. Okay, is that difference clear? All right, good. So in the logistic model, who can tell me what is g of n? Nelson.
Is it r times 1 minus n over c?
Correct. How does that look like? Let's say as a function of n.
Is it exponential?
Well, I don't know. What kind of function is this? Is it an exponential function? We're not talking over time. We're talking just plotting the function g of n. What is it?
Linear?
It's a linear function. That's right. What slope does it have? Is it positive or negative? Negative slope, right? So it's decreasing. It starts out where? When n is equal to 0, right? Starts at r. Okay, and it starts going down, right? Okay, and where does it become 0? Krista?
Negative r over c. Is that right? No, we just.
Do I hear C? C, that's right. Okay, because when n is equal to c, right, you set it in here, and this becomes 1, 1 minus 1 is 0. Okay, good. Now you're waking up. Okay, So why do you think that, if you were asking biologically, intuitively, why does it make sense that the intrinsic growth rate is going down? Why is it going down? Why is it always going down?
Because as the population grows, there's more crowding.
Exactly. There's more crowding, there's more competition, there's the same amount of food and the same amount of space, but things get more crowded. So in a sense, the happiness level of the ability for the giraffes to reproduce, the individual giraffes, goes down. Okay? So G of n goes down due to competition for food and space. Okay. Now, I just want to say one last thing about this type of function, and that is something called the Ali effect. Once again, we have a population model of the form n prime is equal to n times g of n, okay, where g of n, again, is the happiness level of the individuals, or the intrinsic growth rate. Okay, and I want you to think of a situation where G is not always decreasing, unlike in the logistic growth model. Think about a situation where G does this. How can that possibly happen? Yes?
A fresh population on an island, like you just put like 2 or 3 pigs.
Okay, you put 2 or 3 pigs, okay, in an island, and then?
Let them just go crazy for a while. They're going to go up.
They go crazy for a while? Okay.
And then come back down. Because then they're overpopulated, right? The island.
But that still sounds to me like well, first of all, I'm not sure. You said that the population goes up because the pigs go crazy and then the population goes down again. But notice, this is n. This is not time. So I'm not talking about a population that first goes up and then goes down. Right? So right now, actually, I would not know how to describe a population of pigs that first goes up and then goes down over time. Because remember, we only have one variable. Remember we said that that dynamical systems in one variable always are monotone. So if they start going up, they keep going up forever. They might stabilize to a certain point, but they're not going to go down. So if we wanted to make a model of pigs that go crazy and then die and go down, we're going to need what? Predator, yes. Another variable, right? We could not write a model of pigs going first wild and then dying off without including another variable. For example, the grass or another predator or something else. Just by themselves with a model of just one variable, we'll never do that. Okay, Patrick.
Could the parabolic curve be described by, let's say it's like a community animals where there's a group of them and they thrive better, but once the group reaches a certain size, there's still that competitive factor, and so the rate of their
Excellent.
happiness drops?
Yes, that's absolutely right. So you could have a population of animals that are social in some sense. They need each other, right? So if there's too few of them, they're not happy. If there's more of them, they're actually more happy. Even though there's more competition for food and everything, they're better off than if there's too few of them. Can you think of a specific example of that? Buffalo? Yeah. Okay. So I guess you can imagine a buffalo that is just not happy because he doesn't have friends, I don't know, to hunt or something. That can very much happen. But buffaloes don't hunt, right? Yeah, okay, never mind. They hunt grass. Okay, I gotta tell you a joke here. So there's a okay, so there's a farmer and this mathematician comes in. It's a mathematical biologist, right? And he comes and says, you know, I can count, I can write a mathematical model that can count exactly how many sheep you got. And if I can tell you how many sheep you have, you'll give me a sheep. And the farmer says, okay, yeah, he had a lot of sheep. So the mathematician writes down this model and makes a prediction that's very precise, you know, and measures the, I don't know, something about the system, and then finds out what the exact number of sheep is. And then the farmer is, okay, you can take a sheep. So the mathematician takes a sheep. And then the farmer says, so now I can tell that you're a mathematical biologist. And the mathematician says, why? Because you took my dog. Yeah. So, anyway. Okay, so, right, so, fine. So, buffalo, good example. Another example of this actually could be, oh, Mike, you want to say something?
Wolves.
Wolves, okay, wolves.
Some better in packs, but if there's so many wolves, they'll end up competing for the resources.
Exactly, that's great. So if there's only one wolf or two wolves, they're not going to be as effective, right? Or another animal I was thinking is some animal that lives in a desert. For example, if the desert, the desert is very big and their populations are always low, if they get too low, they cannot find each other. So they might die off because they cannot pair up. Okay, there needs to be some kind of critical mass for the population to actually be able to reproduce. Okay, so any situation where the population, where this function first goes up and then down, is called a Lee effect. Okay, so a Lee effect is a phenomenon where g of n first increases and then decreases. Okay, great. So example, and we heard buffalo. Well, actually, I like Patrick's example with the wolves.
I'm Michael.
Oh, sorry, Michael's example. No, I thought it was Patrick's. No, you said. Never mind. I know you're Michael. Okay. Okay, so it was Mike's example. So wolves who need to hunt in packs. Okay, so do you guys have any questions? Yes. Oh, actually, Brian.
You can go first.
Okay, Mike.
So aside from looking at like our old model and saying a happy giraffe is a lonely giraffe, how do we know that we need a new model?
What do you mean a happy giraffe is a lonely giraffe?
Well, in the old model, you have the happiest giraffe is all alone, and the more giraffes there are, they get increasingly unhappy.
Good. Yes. So what was your question again?
How did we know that we needed a new model? Was it because of that observation, or?
Good question. When you're actually doing modeling, so the question is, why do we need a new model? Why not just stick to the logistic model? So say that you're modeling a population and you're trying to quantitatively reproduce the data and it doesn't fit, okay? So you're thinking maybe there's something wrong with the model, okay? And so you try to incorporate more information about what you know about the animal into the model. This might be either A, because the data doesn't fit, or B, because you just want to make a better model. You just want to make a cooler model. Of course, it's important to have judgment into what to include. Remember, we talked about this. This really should be the theme of modeling in general, is that there's this balance between a model that is too simple and doesn't tell you anything useful because it doesn't include enough information, and a model that is so complicated that it's not useful either, because it has all this stuff in it that you can't really do anything with it. Okay, so you really need to find a happy middle between a model that is informative, it's complex enough to be informative, but it's easy enough to analyze. Okay, so by just changing the shape of this function g, we can incorporate a Lie effects. So it's good. It's like not a very high price to pay for what we're getting. We're incorporating this additional ecological information. An example of a Lie effect quantitatively could be a function. Could be a function or a system n prime equals g times n times g of n, where g of n is r0 minus alpha times n minus eta squared. So this would be n here, and here is g of n. Now, what shape does this function have?
Variable.
It's a parabola, okay? It's pointing up or down?
Yeah.
It's pointing down, okay? It's been shifted to the right by eta, and it's been shifted up by r0. So basically, you take your parabola, flip it down so it looks like this, move it to the side by eta, and then move it up. And this alpha serves as a way to make it wider or narrower. So there you go. Okay, and hopefully the rate of growth is still positive here. I mean, alpha cannot just be anything. Ideally, the rate of growth is going to be still positive. Otherwise, it's going to be very hard to start a population. Okay, do you have any questions about Lie effects or single variable population models? Brian?
You said that you need additional variables to have an Lie effect?
Additional variables? No, actually that's not quite what I said. Brian also?
Wilson.
Oh, sorry. Where's the other Brian? Oh, you're Brian. Okay, sorry.
Oh, I
So,
understand.
you guys don't look alike too much. So Wilson was talking about a population model where you have a number of pigs that start first growing and then decreasing in population over time. Okay? So for that, you would need a different variable, an additional variable to the pigs. This model does not have that property.
Yeah.
Just to be sure, just to be clear, even with a Lie effect, even with an Lie effect, you still converge towards some value and stay there. Population itself is not going down. It's just this graph that goes down. Right? Okay. Now, what's the carrying capacity in this model? What would you say? Just by looking at this thing here, what would you say is the carrying capacity, that dotted line over there? Brian? Okay. For this model, where G has this form, where would you say, or how would you describe the carrying capacity? Or not? Okay. Well, actually, you can. Let me give you a hint. The carrying capacity in this model is, in the logistic model, is C, right? And where can you see C in this graph? It's down here, right? It's where the growth rate per individual, the intrinsic growth rate, becomes 0, right? So it would be the same thing actually here. Exactly. Wherever the graph hits the x-intercept, that's the point where the intrinsic growth rate becomes 0. And if g of n is equal to 0, that means that this function is also equal to 0, so we're at steady state. Right? And if we're at steady state, then the population doesn't grow. In fact, the population starts converging towards that value. So qualitatively, if you just plot the function over time, it looks actually quite similar to a logistic model. Okay? It's going to be hard to differentiate just by looking at that between a system with a Lee effect and a system without a Lee effect. Okay, good. One more thing. Abdon, what is the intrinsic growth rate for an exponential model? It's constant. That's right. So if you plotted it for the exponential model, you just have a constant. Okay, good. Great. So I'd like to now continue. Oh, yes.
For the model you create here, is it possible to go, because if we go past it, is it possible to go past that line, the carrying capacity, the dotted line you create on this one?
You could, but then you can never go back down.
Right.
If you ever went up above this line, then you would stay above the line. And then the line would not really be carrying capacity because you just went by it and then convert somewhere else.
Okay. Because I was thinking, I read something about the human population, but I think Malthus or something, 3 billion.
The Malthus model, okay.
Is it 3 billion? I'm thinking like if we went, because we did go way past what we assume is the carrying capacity. So I'm wondering what actually would happen.
So with humans, that's a very good question. I mean, you're relating this to real populations, and I think what happens. Well, by the way, the Malthus model is a famous model, especially back in the day. I think 200 or 300 years ago, maybe not so much, but 200 years ago, Malthus described population growth as exponential growth, and he said something like, you know, it doesn't matter how big the island, how big the world we live in. Eventually, we're going to run up against this limit, and we're all going to die. You know, so basically, he wasn't aware of the logistic model. He just described exponential growth, and then he said, you know, at some point we're just going to run up against some barrier. Okay, so he actually came up with the exponential model. I think it's even called the Malthus model or something like that. So regarding the carrying capacity for humans, it's extremely complicated, right? Because it depends on all these things. For example, it depends on how good we are at making food, and that is not changing over decades. That's changing over years. You know, if we come up with a new way to make corn or to grow corn that is more efficient, then suddenly we can make much more food in the same space, and we can make food for more people. Okay, so the carrying capacity for humans is a very big question that actually nobody knows the answer. Probably 50 years ago or 100 years ago, people thought you could never reach 5 billion, and now we're over 6. You know, we're still out there, right? So so how many the planet can hold is really it's a big question, and we don't know the answer. Okay. And by the way, the carrying capacity might go down depending on other factors, right? And then you could see things going down again. But then that's because there's other variables influencing the system, not just one variable. Yes?
So you're saying rather than being a constant, the carrying capacity itself could be a function of time?
The carrying capacity could be a function of time, yes. Yes. Just like R could be a function of time in the system. Yeah. Yeah, and you can include those things in your model easily, right? Yeah, so. Yes.
So our carrying capacity is like never defined. It's always evolving. Even do research because of the history of our technology increases. That way we can
Exactly. As you get a better technology, you can essentially create a higher carrying capacity. And this before the population actually reaches that carrying capacity, right? You can change the carrying capacity by using different technology. Yep. Mm-hmm. Okay. So. I'd like to go back to, what is it? Was it your question, Abdan, about the null clients? Okay, so I'm just going to say again what null clients are. So suppose that you have a 2D system. And remember, we're always writing systems in this way. You have, on the left-hand side, you have the growth rate, and the right-hand side, you have some function of the states. Left-hand side, we have the growth rate. Right-hand side, we have a function of the states. One technique that you can use to study the system is to solve this equation. 0 equals f of xy. It's called the x null client. It's a set of all the states xy such that x is not growing. Only y is growing at that point. Suppose that that line looks like this. By the way, it doesn't have to be a function. It could look like this. This is x prime equals 0, aka the x null line. Okay, at all those points, because the population x is not growing, the vector field is vertical. In other words, the population is either going up, or directly down. Okay, now we don't know if it's going up or down. The same thing, but we'll figure it out in a moment. The same thing you can do for the g function. This is y prime equals 0 or y null line. So at each of these points, the vector field is horizontal. Okay? Now what you can do to figure out the direction of the arrows is to evaluate the vector field at specific points. For example, you look at this point right here, whatever it is, I don't know, 5, 10, 5, or whatever it is. You evaluate the vector field at this point, and you calculate that x prime equals 0, y prime equals 5. So that means that the vector is increasing. Simply by evaluating the function at this point, by evaluating these functions at that point, you can tell whether the function is increasing or decreasing. So let's say it's increasing. Okay, now what happens when you cross this null line? When you cross this null line, you change the sign. Now the reason for that is the following. As we were saying over there, this is a set of points where y prime is equal to 0. So generally, one side of the plane, let's say the right-hand side of this green line, is going to have one sign, y prime is bigger than 0, and the other side of the line is going to have y prime less than 0. Right? So whenever you are on this side of the green line, the vectors are positive, are growing up because y prime is positive. And as soon as you cross it, you're in the regime where y prime is negative, so you're going down. And similarly, this is going down, and this is going up. Yes, Natalie?
If a certain null line has like 2 lines, does it cross when does the vector field change when those lines cross?
Good question. So it's quite possible that the null line is made up of more than one line. For example, this could be part of the y null line. This line right here could be just part of the same green line, part of the same y null line. In that case, we still have the same situation. We don't change direction or anything because it's the same explanation as before. You only can change sign when you're crossing the null line, but we're talking about the other null line, not the same null line. Okay? All right, so similarly here, you take a point, you evaluate it, and you find out, for example, that you're increasing. So the vector field points that way, and that means that it also points that way here. Okay? But as soon as you cross the other null line, you change the sign. And as soon as you cross it again, you change the sign again. Okay? What happens at the intersection of the two null lines? You have a steady state because on the one hand side, we know that this point is on this null line, so the x component is 0. On the other hand, it's in the other null line, so the y component is also 0. So that means that it's a steady state. Okay? So what can you tell about this particular system? It's a spiral, that's right. Now, what you don't know is whether it's spiraling in or it's spiraling out. You know it's spiraling, but you don't know the stability. It could be spiraling in or it could be spiraling out.
Can it just be a center?
Sorry?
Can it just be like a circle instead of a spiral? Like center?
It could be a center, yes. It could actually be periodic oscillations. Yes. So from looking at the null claims, you can, first of all, you can tell the steady states, which sounds obvious, but there are some systems where it's actually quite hard to figure out the steady states. So the null claims, drawing the null claims actually helps quite a bit. Second, you can get an idea. For example, in this case, we know it's oscillatory. If you want to know whether it's stable or not, you can look at the Jacobian of the system at this point, at the linearization, right? If the, for example, suppose that we linearize this system. Well, let's call this thing xy prime is equal to j times xy. Linearization at a steady state. How can you tell in the 2D case whether it's stable or not? You guys remember this?
If the trace is less than 0 and the determinant is stable.
Okay, so you look at the trace and you look at the determinant. The trace is the sum of the diagonal values. Determinant, you know what it is. If this is less than 0 and this is bigger than 0, that means that it's stable. So for example, if you calculate this determinant and the trace at this point, and you find that these things are satisfied, on the one hand, you know that it's stable. On the other hand, you know that it's spiraling. So what can you conclude? You can conclude that it's a stable spiral. Okay? Yes, sir.
How accurate do you need these on the exam?
How? Sorry, how what?
How accurate the maps for the?
Well, it's a cartoon, so it doesn't need to be quantitatively precise. But for example, whether it's a stable spiral or unstable spiral is a very different answer, right?
Yeah.
So that, you know, I would hope that you guys will get something like this correct. But it doesn't have to be, you know, like the actual values of the arrows or anything. That doesn't. It's because it's a cartoon. It's not so important. Mike.
From just the picture you've drawn, can we tell what the stability is and the other steady state is? It looks unstable.
Looks unstable to you? That's a good question. Yeah, I don't know. I would actually, just to be safe, I would just take the calculate the Jacobian at that point again. Or it could be a. Actually, no, it's not spiraling, right? You're right. It's not spiraling in this case. Yeah, you're right, Mike. So did you realize that it's not a spiral? Okay, so not a spiral, and the arrows are pointing that way, and the arrows over here are pointing this way. So my guess would be that it's actually a saddle, and that it does something like this. Okay? Now notice that, just to be clear, and this is a common confusion, just like it was a confusion over there to have populations going down, up and down again. I think this is a common misconception. It could be a misconception to try and draw the solutions somehow following the null claims. For example, if you drew a solution that did something like this, okay? That's not the correct solution, because this thing doesn't really tell you anything about the, you know, it's not, the null claims themselves are not solutions. Okay, let me put it that way. The null claims are analysis tools, which is different from solutions. Okay, and then the graph can get very messy. You know, if you start drawing all these different arrows, what I would suggest in that case is to draw a different graph, where you would just draw, let's say, the steady states and the dynamics. Something like that. Okay, awesome. Any other questions? Okay, we have 3 minutes. So maybe I'm not sure if I'm going to have time to talk about your example, Mike. What about we leave it for next time? So basically, we're talking about an example where the Hartman-Grobman theorem fails to apply, right? Where the linearization makes the wrong prediction about the system. And the only way that the Hartman-Grobman theorem can fail, really the main way in which it can fail, is when the linearization is not hyperbolic. Can anybody remind me what hyperbolic means?
The real entries are non-zero.
The what?
So the real parts of the eigenvalues are non-zero.
Right, so there's no eigenvalues on the imaginary line. When there are eigenvalues on the imaginary line, things can get tricky. And so that's an example I actually wanted to tell you, but we don't have time. So we'll talk about it maybe next time, okay? All right.